Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will derive a graphical aid to help us solve all transmission line problems or most of the transmission line problems. This graphical aid or graphical tool is called as Smith chart. It was invented by an electrical engineer from US. His name was P.H. Smith, and this was invented way back in the 1930s. In fact, around 1939 was when he published this chart. At that time there were no computers, and therefore calculating or solving the transmission line problems was actually very hard because it frequently required us to transform impedances, and we have already seen that to transform impedances on a transmission line, as you move along you will have to solve that particular complicated equation which relates the input impedance, the load impedance, the characteristic impedance and the length of the transmission line through that complicated formula. And if you have to do it repeatedly, that would be very tedious for someone to do in the absence of any computer. Today computers are faster, they exist, and first of all they exist and then they are very fast. So you could do all these problems instead of using a Smith chart on a computer. But then the advantage of having Smith chart or learning the Smith chart technique is that it provides you a graphical understanding of how the impedances are transforming along the transmission line, okay, and interconnected transmission line. So in a complicated circuit, especially in a microwave system where you will have multiple subsystems, these subsystems will be connected by wires which will act like transmission lines or interconnects, and the impedances keep changing as you go from one point to the other point on this complicated microwave circuit, and Smith chart helps us find these changes along the impedances in a graphical way. It does not always give you a very accurate answer, okay. For the accurate answers you should use the equations, solve those equations on a computer, maybe you write some programs in one of the favorite programming languages that you know of. But then the advantage of having Smith chart is that although it does not give you very good accuracy, okay, it still gives you reasonable accurate values, and most importantly the graphical understanding of how impedance is changing. So let us do the following. Let us first understand the basics of Smith chart, and then in the next few modules we will look at the applications of Smith chart. So this module is trying to help you in understanding the basics of Smith chart, the origin of the Smith chart, and let us begin by actually noting down a particular relationship between the generalized reflection coefficient and the impedance of the transmission line along any point on the transmission line, okay. What is this generalized reflection coefficient? I know that if I consider a transmission line, which be that this is a transmission line, and then I terminate this transmission line with a load impedance, okay. So this piece is the transmission line terminated by this load. In general the load would not be equal to in magnitude or in angle, or in general it would not be equal to the characteristic impedance of the transmission line. We will also assume that the line that we are considering is lossless. So essentially what we are talking is transmission lines characteristic resistance and not really transmission lines characteristic impedance. However, the general trend is to simply use the word impedance, even though we actually mean real value of Z0, that is equal to R0. Although we know that it is real because it is a lossless transmission line, we still continue to call this as a transmission line characteristic impedance, okay. So having said that, and having made the point that whenever you terminate the transmission line with a load, you are not going to be equal to the characteristic impedance all the time. In fact, it cannot be in most cases because the load would be completely different, and your transmission line will not have the exact value. Even if it does, it would be there only at a particular frequency and not over the range of frequencies at which the load is expected to operate. So because of this there will be reflections, and we know that, and we also know how to calculate this quantity called as load reflection coefficient. Load reflection coefficient tells you basically the mismatch that exists between the transmission line and the load at the point on the load itself. That is, I denote the load reflection coefficient, which is a complex quantity, please remember that, as gamma with a subscript L, L standing for load. This is given by ZL minus Z0 divided by ZL plus Z0. In most cases ZL would be complex, and even if it is not complex, if it is real, it would usually be real only at a particular frequency. As you move away from that operating frequency, ZL becomes complex, and hence your gamma L would also be complex. We also know that a complex number can be represented in two equivalent ways. One is called as the rectangular representation, okay, in which you specify the real and imaginary parts of a complex number, and the other would be to specify the magnitude and the angle with respect to usually the x axis. This second representation is called as the polar form of representing a complex number. And since gamma L happens to be a complex number, we can equivalently represent this by the so called rectangular form or in the polar form, where for the polar form I specify the magnitude of gamma L and also specify the angle phi L. Now in Smith chart, all impedances, whether it is load impedance or source impedance or the line impedance that you would consider along the transmission line, all impedances are normalized. Normalized to what? They are normalized to the characteristic impedance of the transmission line. Why is this so? The answer is very simple. If you were to actually put down the real values of ZL or the impedance, line impedance at any point, you would then need a large number of Smith charts, because if you start changing the characteristic impedance of the transmission line by using or employing different transmission lines, then you need different Smith charts. Okay. So this problem is overcome by normalizing all impedances on the Smith chart. So every impedance that you plot on the Smith chart, which we will see later on, is actually normalized to the characteristic impedance of that particular transmission line characteristic impedance, which is Z0. Okay. If you change the transmission line, no problem, because you again take the impedances, normalize it with the new value of the characteristic impedance of a different transmission line. So this is just a way of us to use a single chart, a universal chart for any type of transmission line whose impedance is Z0, and if the impedance is different, you simply normalize every impedance by the characteristic impedance Z0. Okay. So all impedances are normalized. I can actually obtain or write this gamma L in a slightly different fashion, in the sense that gamma L can be written as ZL divided by Z0 minus 1 divided by ZL divided by Z0 plus 1. All I did was to take this equation and then divide both sides by Z0, and now I will introduce a normalized notation, okay, or a notation to denote normalized impedances. This notation of having an over bar denotes the normalized impedance. So I have ZL bar minus 1 divided by ZL bar plus 1, okay, which could further be equal to gamma LR plus J gamma Li, right. So we will come back to this later. This is the load reflection coefficient, but on a transmission line I can always find that there is some incident wave which is propagating along the positive Z direction, or it is propagating from source to the load, and then there is a reflected wave, right, which is propagating backwards, and we can define the reflection coefficient at any point on the transmission line along, at any point Z along the transmission line by calculating the ratio of the reflected voltage to the forward going voltage. So Vi plus would be the forward going voltage, Vr minus would be the reverse going voltage or backward travelling voltage. What are these expressions? We know that reflected voltage can be expressed as the incident voltage which is multiplied by the load reflection coefficient gamma L, right. This is actually V0 plus e to the power plus j beta z, because this is travelling in the backward direction, and Vi plus is the incident voltage, which we can write as V0 plus e power minus j beta z, because this is travelling along plus z or in the forward direction. Please note here that we have considered lossless transmission lines. Clearly we can remove this V0 plus and V0 minus and cancel that, and what you get is the load reflection coefficient gamma L multiplied by this parameter e to the power j 2 beta into z. Okay, let's rewrite this one. gamma at any point on the transmission line is given by the load reflection value or gamma L multiplied by e to the power j 2 beta into z. In fact, the line voltage, that is voltage on the transmission line, is simply given by V0 plus e power minus j beta z, which is the forward going voltage, plus 1 plus gamma of z, as we have seen in the earlier modules. I can also write the line current. Line current will be V0 plus e power minus j beta z divided by z0 1 minus gamma of z. This also we have derived in the earlier module. Okay. Look at this gamma of z. If I imagine that z is changing, z is varying here in this expression, what would happen to gamma of z? Clearly gamma of z is varying, but what will happen to magnitude of gamma? Magnitude of gamma will be equal to the magnitude of the reflection coefficient at the load itself, because when you take the magnitude on these two, to this quantity, you will see that the magnitude of j2 beta z will go away. Okay, it will be equal to 1. Whatever the phase angle of gamma L it might be, that would also go away because of the magnitude operation, and what you end up is a very interesting relationship which tells you that the magnitude of the reflection coefficient at any point on the lossless transmission line will be equal to the magnitude of the load reflection coefficient. How about the phase? If you go back to the phase relationship, we know that gamma of z can be written as magnitude of the reflection coefficient, I can go back to that, and e to the power j 2 beta z plus phi L. This phi L is the phase angle, okay, of the reflection coefficient gamma L. Now, how do I represent this particular complex number on the complex gamma plane? Well, let us first draw the complex gamma plane. Okay. On the x axis or on the horizontal axis, we write the real part of gamma, okay, and I do not keep carrying around this z factor. I just assume that whenever I speak of reflection coefficient, I actually mean reflection coefficient on the line. Therefore, I can write this as real part of gamma, which we can denote by gamma with a subscript of r. Similarly, on the y axis, I will have the imaginary component written of the reflection coefficient, which we will denote the imaginary part as gamma with a subscript I. Now, let us begin by considering what happens at z equal to 0. Please remember that z equal to 0 corresponds to the load location, correct? Z equal to 0 corresponds to the load location, and z axis is actually measured positive from the load, but when you go backwards, that would actually correspond to negative values of z. That is, the values of z here are all negative values of z. Z is less than 0 here. So, please note that this is our convention of representing the coordinate along the transmission line. Okay. Now, first at z equal to 0, whatever we obtain gamma of 0, that would be just the reflection coefficient of the load itself, which will have some amount of magnitude. Okay, let us say this is the magnitude that I have, and I can write an arrow indicating the length of the arrow will be equal to magnitude of gamma L. Okay, so the length of this fellow will be equal to gamma L. Also note the angle that is made here with respect to the real axis. That angle will be the phase angle phi L. Okay, so what we have successfully done is to represent the polar form of the reflection coefficient at the load in the complex gamma plane. So, this is the complex gamma plane. Okay. If you project this line onto the real and imaginary axis, you will actually end up with the value of gamma LR and gamma Li here, okay, which is very obvious. So, we will not write that one at this point. Okay. What happens as z changes? Remember, as z increases, right, or rather z goes from 0 and then as you go away from the load. So, as you move away from the load towards the source, z value increases in magnitude, but its sign is actually minus. So, what it means is that 2 beta z will increasingly become larger in magnitude, okay, as the magnitude of z increases, that is you move away from the load, 2 beta z increases, but it will increase in the negative direction, that is you will actually get minus 2 beta z, right. So the value increases but you get a minus 2 beta z. So your total angle here, which would be changing, so this becomes negative here as z increases, or as you move away from the load towards the source, this becomes negative. This negative value plus some, maybe initially we will assume that this is phi L is positive. So positive plus some negative value, the total value of this angle is actually shrinking, right. So you started from here, which corresponded to the reflection coefficient at the load, but now after traveling a certain distance z, you end up with the same magnitude but at a different angle. Okay. So let me expand this particular graph because it's kind of interesting to look at. So this is the complex gamma plane, this is gamma r and this is gamma I, and we started off with the amplitude here or the magnitude of gamma L at this point with an angle phase phi L here. As z increases, so this was actually at z equal to 0, at some value of z away from the load, right, towards the generator, your reflection coefficient would remain the same magnitude but its angle is now different. The amount that you have rotated from z equal to 0 to some z equal to minus d would actually be equal to minus 2 beta d, because the total angle now is given by phi L minus 2 beta d. So what is important to note here is that as you move towards the source, as you move away from the load and towards the source, okay, you will be moving along this particular circle whose magnitude would remain constant and it would be equal to gamma L. So magnitude remains constant and you would be moving successively along or successively on in the clockwise direction as you move away from the load. So this is moving away from load towards source, or in the older terminology this was called as generator. Okay. So this is the movement along the transmission line away from the load and towards the generator. So you would actually move like this, right. Okay. So this is the complex gamma plane, and you can actually consider or think of different circles. For example, I might have a different value of gamma L, so that would correspond to a different circle, then I would have another circle, then I would have one more circle and so on. What is the maximum radius of this circle? The maximum radius of this circle would have to be equal to 1. Why? Because the maximum value of mod gamma L can only be equal to 1. So your magnitude of gamma L will be equal to 1, and that would be the largest circle that would be possible. Okay. Along with initial value of phase angle that is given, you can move a certain distance which is actually equal to minus 2 beta d in order to find out, or in order to land at the new value of the reflection coefficient gamma, and from that new value of the reflection coefficient, maybe for example in this case this is the new value of gamma at minus d, you can use the relationship gamma of minus d is equal to, or so since you already know the relationship for gamma of z, which was given by this magnitude and this expression, you can also go back to this line impedance or the line voltage equation. In fact, find out the line impedance of this one, which would be just the ratio of these two multiplied by z naught, and obtain a simplified equation over here which will relate gamma of z and the impedance. That is what I am trying to tell you is that given the line impedance, given the line voltage, given the line current, you can find out what is the line impedance at any point on the transmission line, and you would see that the normalized line impedance would be equal to 1 plus gamma of z divided by 1 minus gamma of z, because you simply divide these two left equations, and then that ratio, this z naught will go on to the top. This would be the line impedance, and that line impedance will be divided by z naught in order to normalize the line impedance. Okay. So if you know gamma of z at any point on the transmission line, and you can now know how to do that one by following this particular arc, okay, you can figure out what would be the line impedance. However, this process is still a little bit tedious because it involves a formula. So what this P.H. Smith came up was a very interesting scenario. Okay. In that, what he considered is this basic quantity. Suppose we restrict ourselves to passive loads, which means that your value of mod gamma L cannot be exceeding 1, okay. And what possible values of resistance and reactance that you can find of. Any impedance, right, the complex impedance will have a real and the imaginary parts. The real part will be the resistive part and the imaginary part will be the inductive or the capacitive susceptances, right. So, this reactance part will be there. The reactance part has a sign associated with it. If it is positive, then it would be inductive reactance. If it is negative, then it would be a capacitive susceptance, okay. Also, for the kind of loads that we consider and the transmission lines that we consider, we need to always have R greater than 0, okay. R less than 0 actually corresponds to negative resistance devices, and negative resistance devices do not actually exist for passive loads. They can be made to exist for a active load, or in active load resistance can be considered to be negative, and negative resistance means actually gain. So, positive resistance means loss, negative resistance means gain, okay. So, for now we will restrict ourselves to only R greater than 0. So, this is my complex Z plane, that is, this is the complex impedance plane, which can again be thought of as normalized value, okay. So, normalized again with respect to Z0 of the transmission line. So, this impedance is given by 1 plus gamma of Z divided by 1 minus gamma of Z, thus relating the impedance and the reflection coefficient values at any point on the transmission line. So, you might be seeing lot of Z values being used. So, please excuse this notational inconvenience. I hope the context is making it clear which Z we are talking about. The Z in the bracket corresponds to any point on the transmission line. The Z outside corresponds to the impedance, and a bar over that corresponds to the normalization that we have done with respect to Z0 of the transmission line. So, this equation we know, right, and we also know that given gamma L, we can find out what is gamma of Z at any point on the transmission line, because this simply involves moving a distance or moving an angle by a value of minus 2 beta Z, or if I forget the sign, then you simply need to move by 2 beta Z value in the clockwise direction, okay. So, this relationship is actually a one-to-one relationship. Why? Because I know what is gamma of Z, I can find out what is the value of normalized impedance. Also, the normalized impedance will be completely this region, right. So, this entire region is possible values for Z of Z, okay, the complex Z value, which we will write it as R along the real axis and X along the imaginary axis. So, this is R and X. Here would be the inductive capacitances, or sorry, inductive reactances, and this one would be the capacitive susceptances. So, what Smith did is to consider this Z plane, and by knowing this relationship, okay, this relationship can be inverted to write one more relationship. I will just write that one in a few minutes, but then he converted this entire rectangular region, which is to the right side of the complex Z plane, this entire right half, into a circle, okay, on the complex gamma plane, where the axis was gamma R and gamma I, with the maximum value of the radius being equal to 1, signifying that the reflection coefficient for passive loads cannot be more than 1. So, how can this magic of the entire right half being converted into the region within the unit circle happen? This magic happens by what is called as bilinear transformation, okay. This is one method in which a line in one complex plane can be converted into a curve in the other complex plane, and this is the example of bilinear transformation, which relates Z and gamma, okay. You can invert this relationship, and that inversion is also important, because gamma of Z can now be written as Z bar minus 1 divided by Z bar plus 1. Again, I will drop the subscript or drop the argument of Z. I understand that left hand side is also a function of Z, the right hand side is also a function of Z, Z being the distance or the coordinate on the transmission line. So, you can invert the relationship, okay, which will relate the reflection coefficient and the normalized impedances. So, what is the use of these two? Well, I know that the complex impedance can be written as R plus jx. I also know that this gamma can be written as gamma R plus j gamma I in the rectangular form, right. So I can write in this particular fashion, and then what I will do next is to try and relate this r with gamma r and gamma I and x with gamma r and gamma I. To do that, we will start with this relationship, that r plus jx, which is the complex z value, the impedance value. So let me write this down. This is impedance, okay, except that we have written this impedance, in this complex impedance, in the rectangular form. So this would be equal to 1 plus gamma r plus j gamma I, where gamma r and gamma I are the real and imaginary parts of gamma of z, divided by 1 minus gamma r minus j gamma I. Please note that this relation is nothing but 1 plus gamma by 1 minus gamma. Please also note that it is not the magnitude, therefore do not confuse this with the standing wave ratio expressions. Okay. So you can write this, you can multiply the complex numbers from the complex conjugate of the denominator, and after you have done that one, what you will obtain is r plus jx equal to, I will write down the expression here, now you can separate the real and imaginary parts of this right hand side expression and equate it to r and x, and then do a little bit of an algebra. It is little tedious, but it is straightforward. So do a little bit of an algebra so that you end up with the relation for r in terms of gamma r and gamma I, and the relationship is that gamma r minus r by r plus 1 magnitude square plus gamma I square will be equal to 1 by r plus 1 magnitude square. Similarly, equating the imaginary parts and inverting the relationship and carrying out a little bit of an algebra will give you another relationship, which is gamma r minus 1 square plus gamma I minus 1 by x whole square equal to 1 by x square. Please note that in this relationship, it is only gamma r, gamma I and r are involved. Gamma r and gamma I are in the complex gamma plane, r is the resistance or the normalized resistance or the normalized real part of the complex impedance. In this equation, you have the complex gamma plane related to x values, x being the reactances. Okay. We will now in the next module actually build up the Smith chart by understanding these equations. If you remember or if you recall, these equations are equations of circles. For example, if you consider this equation, which would be called as the constant r circle, because this relates the value of r, okay, this constant r circle values are given by, or the constant r circles have a center of r by r plus 1 comma 0, and they have a radius of 1 by r plus 1. Similarly, this would be the constant x circles, where the center is given by 1 comma 1 by x and the radius is 1 by x. As r changes, the center changes and the radius changes. As x changes, the center changes and the radius changes. If you put or if you plot both these equations on the same complex gamma plane, you would end up with Smith chart. It is as simple as that. I would of course suggest that you derive these equations because they are tedious, and therefore I have avoided deriving that. So in the next module, we will build up the Smith chart. Thank you very much.